With atomic units, we can now express some of these real systems, atoms like hydrogen and, as we'll see, helium, in a much simpler form. So let's see what this looks like. I've again written down this Hamiltonian for the hydrogen atom up here at the top. Then you can see this is all done in spherical polar coordinates, so it's a fairly complicated expression that involves several physical constants, both in the kinetic energy part and in the potential energy part. All right, now in atomic units, once we put things in atomic units, this is equivalent to saying that constants like h bar, the electron charge, the mass of the electron, and even the permittivity constant, that all of these constants are equal to 1. Okay, so we're doing it in those constants, so we can substitute 1 wherever they appear up here in the hydrogen atom Hamiltonian. So what does that make this Hamiltonian look like? Well, if we got 1, it's just going to be minus 1 over 2r squared. You can see already a lot simpler there. And I'm filling in the rest of this. It's still a complicated expression in spherical polar coordinates, but we'll see that we usually forego writing all this out. And for the potential term, again, I'm going to have a lot of things cancel. It's just going to be equal to minus 1 over r. Well, that's a lot simpler. Okay, so this Hamiltonian, as we've written it out, there are going to be a lot of different ways that we use to make this look simpler. Okay, one of these might be, for example, all of this stuff down here you may recognize as being simply the angular momentum squared, although we're missing that factor of h bar squared, so I'll put 1 over h bar squared L squared. All right, so that's one way we could simplify it. So for example, we might write the Hamiltonian for the hydrogen atom as something that looks like this. All right, it would include 1 over 2r squared times this ddr r squared ddr, so the radial part of this, plus 1 over 2r squared L squared. Okay, minus 1 over r. So already this Hamiltonian is a lot simpler than the one we've had before. Now this part here, this radial part, we might sometimes write this as sort of the radial part of the Laplacian operator, but it's more common that we might write this Hamiltonian simply by collecting all of the differential terms, so including the terms that are part of the angular momentum here, like this, and the Hamiltonian would simply be written like this. All right, well, this is a lot easier to deal with than all of this stuff up here. Okay, but I caution you, when you write this down, there's a couple of things you need to realize about this. One, there are no constants in here, so this must be in atomic units. And two, this Laplacian is a very complicated operator. That is to say, it takes its form from whatever set of coordinates that you tend to use. So the most obvious and easiest form is to write it in Cartesian coordinates, like this. But it could also be written in spherical polar coordinates, as we've done up here. So the Laplacian operator is a great placeholder, and it makes our expressions look simpler, but it carries with it, I'll say, some hidden complexity that we need to be aware of. All right, so our hydrogen atom looks pretty simple. What do we get for the answers for the hydrogen atom? Well, remember that our energy levels for the hydrogen atom could be written as follows. E sub n is equal to minus m sub e to the 4th over 32 pi squared epsilon squared h bar squared n squared, okay, where the n is a quantum number. So that part we can't get rid of. Okay, but now if I express this in atomic units, well, first of all, I'll note that in atomic units, the Hartree, remember we defined it, Hartree, and I didn't write it in all its formidable glory and detail, but it's equal to minus 1 over minus me e to the 4th over 16 pi squared epsilon squared h bar squared. So we've got most of the elements here over here. And in fact, what we would find is this is equal to minus 1 over 2n squared times the energy of the Hartree. But since the energy of the Hartree is an atomic unit, we can it's just equal to 1 in atomic units. So in atomic units, our eigenvalues for the Hamiltonian of the hydrogen atom are just 1 over 2n squared. All right, so very easy to track the energies of the hydrogen atom when we're in atomic units. But we have to remember that the atomic unit for energy in this case is the Hartree, which is given by this set of complex constants. And it's also useful to remember that it's 27.2 electron volts, or some appropriate number of joules. All right, what if we go to more complicated atoms now, more complicated like helium? Well, remember, helium is a nucleus that contains 2 protons and 2 neutrons, so it has a mass of 4 times the mass of the hydrogen atom. It has 2 electrons, and I'll just draw those sort of out here at different points. So here's an electron out here, here's an electron out here. So that means that we're going to have some additional coordinates for helium that we do not have to worry about for hydrogen. Okay, in particular, let me draw this in a different color. I've got this length here, which I'll call R1. We'll call this electron 1. We'll call this electron 2. I'll have this length here, which is R2. So when I start to write down the Hamiltonian for the helium atom, I'm going to have to include these extra coordinates. But it's more than that. I've got 3 different particles here, and so I'm going to have basically kinetic energy for all 3. Now, we get around this a little bit by eliminating the translation of the entire molecule, the entire atom. So what I can do is, since the electrons are so much lighter than the nucleus, I can effectively approximate this as 1 over, I'm going to make this minus h bar squared over 2 times the mass of the electron times the kinetic energy of each electron individually, which I'll write now very simply as Laplacian 1 squared plus Laplacian 2 squared. Okay, all I've done here is take my expression for the Laplacian, and now I've got twice as many coordinates. I've got x, y, and z for electron 1, x, y, and z for electron 2. I just use these subscripts on the Laplacian to indicate those kinetic energy operators. Okay, I'm then going to have the attraction of electron 1 with the nucleus. So that's going to be electron squared over R1. But remember, the nucleus has a charge of +2. So I have to take that into account, and it turns out it puts a 2 up here in the numerator. I'm going to similarly have the attractive force between the second electron and the nucleus, and that 2 is going to be written 2e squared, but now divided by the distance R2 between that electron and the nucleus. All right, now I'm still not quite done. There's going to be one more term in this Hamiltonian, and that comes about because these 2 electrons repel one another. And we're going to say that they're separated by a distance of R12, but that's going to leave a term that's e squared over R12. There's no 2 there because each of the electrons has a single electron charge. All right, so I have done this kind of half and half in atomic units and non-atomic units. So if I were to put this in atomic units, I'd include these permittivity constants here in the denominator. Okay, so if I write this out simply in atomic units, it'll simply be 1/2 times the sum of the 2 Laplacians minus 2 over R1 minus 2 over R2 plus 1 over R12. And you can see with this very simple presentation in atomic units, we can see all of the essential features that we need to take account of in the helium atom. There's the kinetic energy of the 2 electrons. There's the attraction of 1 electron to the nucleus, the attraction of the second electron to the nucleus, and the repulsion between the 2 electrons. So as long as we know how to read a simple equation like this, and translate it, if necessary, into the more complicated form up here, we can talk about helium and understand physically what it means. Now, I want to note one other important thing about the helium system. And this is something that really is the whole reason for having a separate module on all the atoms other than hydrogen. All right, all three of these particles interact. That is to say, the nucleus, which is the 2 protons and 2 neutrons fused together. So all three particles interact, as well as the 2 electrons. So we have 3 particles interact, so means we cannot separate into smaller variables, into fewer variables. Okay, in the case of the hydrogen atom, we were able to eliminate the translation of the atom, and we simply had one coordinate, and that coordinate was the distance between the proton and the electron. In the case of helium, I can't just have one coordinate like that. I'm going to have a minimum of at least 2. And in fact, because all 3 of these particles interact, changes in one of these coordinates changes the other 2. Okay, so if I were to all of a sudden make R12 bigger, unless I were keeping the electrons on concentric circles about the nucleus, their distances with the nucleus would change. If I change one of these distances, I'm going to change at least one of the other 2. So, in other words, changes in one coordinate can't be done independently. Like they can, for example, say in spherical polar coordinates, I could change the radius without changing the 2 angles, or I could change one of the angles without changing the other angle or the radius. In that way, I can create separable differential equations. But for this reason, I can't create a separable differential equation that deals with a 3-particle system. For this reason, helium cannot be solved exactly. And in fact, what we're going to have to do is develop some approximation techniques that allow us to develop solutions for the helium atom that give us some reasonable results for their energy levels and other properties. That's what we'll be talking about for the remainder of this module.